Another really cool thing that your lab does, or the whole Regenerative Medicine Institute does, is you focus on bioprinting organs. And I think that's one of the coolest things that is, even being done, because like 50 years ago, or even 20 years ago, this wasn't even, I guess, a possibility. But now, I guess research has advanced to a point where we're looking at new ways that things are being done. And from my understanding of bioprinting, it works kind of like a 3D printer. You basically put cells, like stem cells, into an ink cartridge, and you program the 3D printer to 3D print this structure. And and it knows that by taking like a CT scan of a kidney or I don't know, or bladder or something, and then it lays down layer by layer to try to build up that structure. Is that right?
Yeah, exactly. Right. So let's touch on a couple of things. So number one, if we think about just more hobbyist 3D printing, or even more, I guess, engineering 3D printing, right? There's multiple modalities for that. Right. You could have a resin printer, which is to have a bath and then to cure your structure within that particular bath, and then you've pulled out this high quality structure that you've built. You could have an extrusion base, right? You have your material, a plastic typically, and your 3D printer heats that up and starts printing out lines and dots of 3D printers as it builds upwards, right? More pushing out with pressure. Let's see what else. You've got inkjet printers. I know that was one of the first bioprinters, right? Was to kind of use an old inkjet printer and deposit tiny little droplets and start building up in 3D space. But yeah, you're right, right? This is working essentially the same as one of your different modalities of 3D printing. I wanted to bring up there that even in hobbyist 3D printing, there are multiple modalities to highlight that, not just at the Institute, but across the world. There are a bunch of people tackling 3D bioprinting, if we think about adding biology to this complex issue, with multiple modalities. So it's not just as simple as, oh, there's one way to do this, go. There's a lot of great companies out there that you can buy different bioprinters from, or you can make one in-house. And certainly, Wverm has made some of our own as well. And then there's I think, kind of your next big considerations on this. You mentioned some stem cells, but we might be able to work with more differentiated cells, particularly if we're thinking about printing and then implanting. Now, a little easier said than done. So I'm going to take a step back from cells and let's talk for a quick moment about biomaterials. And so, how do we get cells to stick to something? So when I was talking about muscle biology, I mentioned the extracellular matrix. And I like to tell little kids that I teach think of like Spider-Man's webs holding your cells together. And that's not too inaccurate there. And so we kind of think about that as well with the bioprinters, right? What should we use to hold, what scaffold, what support material should we use to hold the cells and stick them together? We could try to use a natural extracellular matrix, that natural scaffold, and 3D print with that, right? We can decellularize a piece of tissue, take that scaffold, grind it up, reconstitute it with some water, for example, and then print out with that. That's an option. Another really popular option is hydrogels. So these different, primarily water-based chemistries. We can use plastics. Ceramics is popular for bone engineering. And the trick, I think, with this is to think about what your cell type is, right? The stiffness of your material and how accurate that is to the human body, right? I want my osteoclasts and osteoblasts, my main bone cells, to be printed on a harder scaffold because that's what your bones are, right? They're a much more stiff material. As opposed to something like bioprinting skin, well, if I try to use that same support material, the cells aren't going to like it very much, right? So I need to think about a softer material, something like a hydrogel. Then we get to the next issue of maybe natural versus synthetic. A lot of these synthetic scaffolds, these synthetic polymers are beautiful in that we've got full control over them, right? We can very accurately replicate that chemistry. We can make batch to batch the exact same way and use that every single time. And that's great. That offers some really wonderful engineering and manufacturing control there. And some of these the body will tolerate. There's an idea that's popular with biomaterials of getting things to hide from the immune system. Sometimes that's preferred, right? If we do not want this structure to be degraded, maybe we want to hide it. But I think what's really popular with bioprinting is to use something that specifically does not hide from the immune system, but rather we know how quickly the immune system decides to attack it. The idea behind this is, okay, we've bioprinted with, for example, a particular type of plastic, maybe polycaprolactone, PCL, it's a real popular one. We've used that support structure, we've attached cells to it, and we implant it into the body. And we know that based on the thickness that this structure, your body will slowly degrade in a non-toxic fashion, and it's going to take, let's say a whole year. Well, that gives your cells enough time as that structure is slowly degraded to start producing their own natural extracellular matrix, their own natural connective tissue to stick to each other as that plastic material is safely degraded inside your body. And of course, we can play with the different chemistries there to say, is material A or material B degraded faster or slower, and is that okay for where this is going inside the body? Are the cells going to like it? I think the last component to this is getting a little bit back to the cells. If I were to just throw a bunch of cells into a syringe and expect to print with that, well, that wouldn't work too well, right? They just kind of flow right out. I might have those in media. And so really a lot of times what we're doing is we're printing using a hydrogel. And so that also offers another complexity of what hydrogel, what bio ink you might see in the literature. What should we use, what gel-like material should be used to encapsulate these cells that they are going to survive for several hours in as we use them to 3D print, such that we can load them into a syringe and put pressure from the top of that syringe down and extrude them out without having that pressure or that material be damaging to the cells. Does that kind of make sense?
Yeah. Once you insert these biomaterials into the human body, as far as the immunological response goes, do you take that into consideration before you create a structure, like a biomaterial structure? For example, if you make something out of, let me just guess, like cellulose or something, that might have a better compatibility to like implantation as compared to if you created it with something else, and it could have a worse outcome because it has a greater immunological response. Have you researched that before you implant, whether it's biomaterials or 3D printed structures into the stem cells, or have you looked into that before you start the process?
Absolutely, right? This is why there needs to be, and there is extensive in vivo testing before we're getting to those human clinical trials, right? It's something we're very concerned about, right? Sometimes we want a little bit of an immune response, but we don't want there to be an absolute gigantic mounted attack on this biomaterial. And so just looking at the biomaterial alone and the body's natural immune response to it is in and of itself an entire area of expertise, and extremely important to the field of bioprinting. Yes.
Okay. And then as far as other structures go, because once you 3D print something, from my understanding, it's useful whenever it's like a blood vessel or a tubule or a urethra or something that's simple, hollow. It doesn't have a lot of functional weight to it, versus if you try to like 3D print an organ, for example, you might be able to 3D print a model of it, but that model might not be functionally active, because it may not have the proper blood supply, proper innervation, proper what do you call it, response. So
physiology of the organ.
yeah. So have there been improvements in either your lab to figure out ways to use these bioprinted organs to actually make them functional and compatible with the human body?
Yeah. So what you're getting at, right, is this idea of a more simple hollow tubular organ, or just even kind of hollow organ, which is certainly our most advanced clinical trial products right now. I encourage anybody listening to go look up Dr. Attal's TED Talks, to look up his bladder project. He's got a recent paper out, I think just about a month or two ago, for some wonderful work on an engineered uterus implanted in vivo with successful live births in rabbits. And it's beautiful, beautiful work. But some of these structures with maybe a more passive function, right, of being a urethra, for example, a hollow tube that just has to pass a fluid through, is certainly much more simple than a complex solid organ. And just like you mentioned, Raghu, right, you've got these extra complexities of not just it being a solid organ with a particular function, but now that it's solid, you also have to worry about that vascularization of the tissue, the blood vessel growth in it, as well as the innervation of the nerve cells. It's extraordinarily complex. So the simple answer to your question is, hey, we're working on it. Thinking about how it's going to not just get those two ideas of vascularization and nerve innervation down, but how do we have this organ working correctly? Now, certainly a big focus of our institute is to use patient-specific cells, right? So we want to go and take a small biopsy and try to proliferate those cells in culture dishes or large flasks. If anybody listening has seen a biological clinical manufacturing site, so instead of a petri dish, for those lay listeners that you might have seen in high school, think a large, big flask of cells, giant. We're growing millions and millions of these so that we have enough to grow one piece of tissue with, to grow one organ. I think some of the most recent advancements in this, right, is starting to hit on this idea that you mentioned of what is the physiology. It's one thing to have the right structure, which certainly goes hand in hand with function, as I said before. For example, a kidney, right? We need to have that glomerular structure in order to filter out the blood. But we also have to have the right cell types. We have to have the right cell types that are producing the right enzymes, the right proteins. They have to have also the right function. And so that's something we're constantly looking at in the lab. What is the next big function that this tissue has to take? And how do we get it to that function? Right? How much albumin is produced? How much of, if we think about liver, how much of cytochrome P450 is expressed, right, for the metabolism of drugs? Really, really critical right there. If you're not producing any, well, you don't have functional tissue. Although you might be growing those liver cells, well, sorry, it's not producing the main enzyme, or at least the most popular enzyme that I'm aware of for drug metabolism. It's super critical, right? And then once we solve that problem, on to the next one. Well, what's the next biggest thing? And so your question is not an easy one in that we are focusing on that. We are attempting to get the correct physiology in addition to structure. And that is an absolute must for growing these complex organs for implantation to the human body. But it's something I think that even once we have lots of successful organ implantations of multiple organ types, we'll still be going back to the drawing board for probably at least 100 years, if not longer, as we say, okay, well, we've got it 50% of the way to normal human function. Well, can we get it to 75%? Can we get it to 90%? Can we push these tissues to be completely like your body, to complete normal physiological response?
Okay. And that's, I think, the challenge, or not the challenge, but like I guess the challenge is trying to get it from a model to a functioning model that's accepted. Have you done any research in, for example, different animals? Maybe different animals have similar, organs, but they may function. It might not be as big if you take like a smaller like rat
Yep.
or something, seeing if these 3D printed models work on these smaller animals and seeing the response to that. Has there been promise in that area, like 3D printing a model for a small animal and then seeing if that organ functions in that small animal?
Yeah, I think there's a little bit of a grim joke in biology of, well, we can cure a mouse of anything. We've got these smaller animals. We could do so much with them, but trying to fix that scalability problem is super difficult. Now, thinking very critically, right, if there's a reason we study as scientists mice and rats. They're small, they're easy, they're mammals that are certainly very applicable to the human body. And we have some wonderful models in the field, and certainly wonderful models the FDA will say, hey, if you could do this in just a rat or mouse, this part of the body is good enough to move to human. I think cancer is one of the more popular fields with that, right? If you can grow different tumor types and show that your drug works on some of these established mouse or rat models, you can go ahead and try a clinical trial in a patient. But it's something we're constantly thinking of, right? Let's start with the basics. Let's start with something easy. Can we grow a small kidney? Can we grow a small liver? Can we grow a small tube for, a blood vessel replacement, for your urethral replacement? And let's try it in something small, a mouse, a rat, a rabbit. Really study the function there. And then we're going to go on to the next biggest thing, right? Can we do this in a bigger animal? And if we are successful there, will the FDA let us move to the human trial?
Yeah, yeah. So it's like you have to go at it like from a FDA approved step-by-step basis and follow all the protocols.
Of course. For those listeners that might not be as familiar with the scientific research process, I think that's really important to critically highlight here. We as scientists don't get to just on a whim say, I want to try this, right? We have a lot of respect for the animals that we are very lucky to work with. And certainly anything that we do is going to have positive implications for pet and companion animal health. And we're always constantly asking these ethical review boards, can I do this study? Here is the care and consideration that I've taken in order to ensure that this is the proper study and I have the right rationale. Can I try this? And when they say yes, we are allowed to proceed with any particular animal trial. Whole other level as well when we start to get to a human, right? Then we've got the FDA saying, okay, what information did you find in the animals? What are you seeing now? Let's try this out. Okay, I like that information. It is safe enough. It is ethical enough to try in a human patient. There's nothing that we're doing that we're not constantly internally criticizing ourselves, but as well asking others to criticize us for that ethical consideration. Is this the right thing to do?
Yeah. And another question that I had was, do you think that, for example, if research progresses like it has been progressing, do you think we're ever going to get to a point where, for example, we can combine certain technologies with certain stem cell organs to have a organ that functions better than what we have innately, I know that it's like something sci-fi, something out there, but it does it's something that it's like a question that I have, like, because the point we're at now is like we can print 3D organs. What happens when we combine what happens if we make a 3D pancreas and combine it with some kind of electronic that like produces insulin, that is life-changing to a diabetic, or if we like print a heart that never stops beating, either putting it due to a pacemaker or something like that, and that way you're never gonna have like a heart failure. I mean that's kind of out there, but do you think that that's not outside the realm of possibility?
Oh, that's a great question. Outside the realm of possibility, right now, yes. In the future, I think you make a good point. Probably not. I think I know that we're still a long way away from getting to that normal repair, right? I think we'll easily the next 100 years we'll be working on, can we get these organs working normally, right? Which is not to say that we won't sooner have things in the clinic for you to help, but I think for a long time, like I was kind of previously mentioning, tweaking that physiology, right? Of, hey, we can't grow your liver yet, but we can give you half of one because yours has failed, and that's enough to help keep you alive. Right now, you would have died before. Now you don't need a liver transplant. We keep you alive. We can 3D print you one. Great. So thinking kind of further in the future about that sci-fi question of, well, can we make physiology better? I think that's a really interesting question. I don't have a good answer for you. I think that that's an open opportunity for us to talk, us, the world, to talk about, right? What is defined as normal physiology, right? We've got these clinical metrics of how much, let's think about like what your blood glucose level should be every day, and needing appropriate insulin production to help you maintain that blood glucose level after a meal. What is your different hormonal production like? We know within reason, I think, what that should be, but will that shift in the future? Possibly, right? If we are now if we in the future get to a point where we can say, well, we can bump this up, we can make this better. This is a question that I think is a welcome question for the world, for the public, for ethicists to get together and say, I don't know if we should.
Yeah,
the body is designed one way. Should we keep it like this? Do we redefine normal and make that our limit? At least in the US, certainly, I think pretty much everywhere around the world, we already have restrictions on different forms of research to say, hey, this is unethical. You can't do this. And I don't think it's unreasonable to say that in the future of, hey, we've talked about it. This is, the level of physiological limit you are allowed to go up to when you are making an organ, and you can't go past that. I don't see any reason why we can't determine that.